Okay, let's do a couple of problems which we already know how to do, and let's just see if we can do them using work and energy. So my first problem is the following. Suppose that I take a ball with mass m and I throw it up in the air with some velocity v. We all know what it's going to do. If I throw it straight up, it's going to go up until it gets to some height h, and then it's going to fall back down. And I want to know how high it goes. Okay, what is h? Well, what I'm going to say is the initial value of the kinetic energy is equal to 1/2 mv squared. And the final value of the kinetic energy is 0. Okay? So those tell me what kf minus k initial is. Okay, so delta k, the change in kinetic energy, is equal to minus 1/2 mv squared. But that's got to be equal to the work done. Well, are there any forces on the mass as it moves? Let's have a look at the mass here as it goes up. There is, of course, its own weight, mg, which is down. Okay. And that's the only direction. That's the only force that there is this one force that's down. And we're going in this direction. Okay, so if you like, we could define a displacement vector h this way. So you can see that the work done is negative. The force is constant, so it's just mg, and so the work is just minus mg times the distance traveled, which is h. And so you see, if I now solve for h, I get that h is equal to, m's cancel out, and so it's 1/2 v squared over g. And that's all there is to it. If you go back and solve this problem using kinematics or using Newton's second law, you'll find the same answer. Okay, let's do another problem. I have a mass, let's say it's 10 kilograms, and it's moving along with a velocity right at this instant of, let's say, v equals 5 meters per second. Okay. There's a coefficient of kinetic friction, which is equal to 0.3, let's say. Kind of sticky. And so what's going to happen is, as this guy goes along, because of the frictional force F back this way, there will be an acceleration which is negative, and eventually he'll come to rest. Okay, so here in this case, V final is equal to 0. V initial is equal to 5 meters per second. And so the kinetic energy at the end is 0. The kinetic energy at the beginning is equal to 1/2 times 10 times 5 squared, which is 5 times 25 is 125 joules. I'm assuming that Mr. Swain has taught you that the units for energy are joules, and 1 joule is 1 kilogram meter per second squared, which is equal to 1 Newton meter. Okay? except I made a little slight mistake. Oh no, I'm sorry, this is the kinetic. Okay, so now the change in kinetic energy, which is K final minus K initial, is equal to minus 125 joules, and that has to be equal to the work done. And the only work done here is by the friction. And we can all see, I think, by inspection at this point, that the frictional force is equal to mu n, and in this case the normal force must be equal to 100 newtons, and so this is 30. Okay, so the work is equal to 30 times the distance, which we'll call S. Let me neaten that up a little. Not minus 30S, and so S is equal to 125 over 30 meters. Which is about 4.17 meters. Maybe I should remind you how you would do this problem before, to show you that there at least seems to be a little bit of advantage here. Okay, the way that you would have done this problem before is you would have said, okay, you would have gone through the rules of the game thing, and you would have found out that F is equal to 30 newtons. Okay, and so the acceleration would have been equal to the force divided by the mass. Okay, and it would have been negative if we choose the plus x direction and to the right. So this would have been equal to minus 3 meters per second squared. And then you would have said, okay, the velocity is 0 at the end, and that's equal to v naught, which is 5, minus at, plus at, which is minus 3t. And so then we would have found that the time it takes for it to stop is equal to 5/3 seconds, and therefore the distance it would have gone is equal to 5 times 5/3 minus 1/2 times 3 times 5/3 squared. And now if you do that arithmetic, you will find that you get 4.17. So this is sort of like a one-step problem compared to the way that you would do it the old-fashioned way. Finally, let's do this problem where there's no friction as M1 slides on the tabletop here. It's being pulled by a string, and the string passes over this ideal pulley, and it's attached to M2. And everyone starts off at rest. The initial velocity is 0. So I start off with a kinetic energy of the whole system of 0, because everybody's at rest. The final kinetic energy we'll calculate after we've fallen some distance h, after M2 has fallen some distance h. So this is K initial, K final is equal to 1/2 times M2v squared. But of course, M1 will also have the same speed, v, so it's plus 1/2 M1v squared. So the final kinetic energy is equal to 1/2 m1 plus m2 v squared. And that's got to be equal to the work done. And so now we have to ask ourselves what work has been done on this system. Well, we could look at each object separately. Suppose we look at M1 and we ask, what are all the forces on M1? Well, there's no friction. There's a normal force. And there's the weight, M1G, like this. And there's some tension in the string. And since M1 is moving horizontally, the weight and the normal force don't do any work. So you don't have to worry about them at all. The tension in the string does do work, okay, and the amount of work that it does, okay, so let's just write that as W sub 1. The work done on 1 by the tension is equal to T times the distance it moves, which is H. Okay. Now if we look at M2 and say, what are all the forces on it? Well, there's its own weight, M2G. And there's this tension in the string T like this. Okay, so the work which is done on M2 by the tension, I'll call that W2, is equal to minus TH. So the work which is done by an internal force here, which is the tension in the string, is 0. Okay, so we sort of chalk that up to experience now, and we remember in the future, as long as we look at a system, any forces which are doing work inside that system, those all will end up canceling out. Okay, so finally we're left with the only force that does any net work on the entire system is the weight of M2, and since that is in the same direction as H is, it's a positive work, so that's M2G. Times H. And so now if I solve for V, find out how fast it's going, V squared is equal to 2m2gh divided by m1 plus m2, and so V is equal to the square root of 2m2gh divided by m1 plus m2. Again, you could have done this with what you already knew from previous chapters, but I think if you go back and redo this problem to find out how fast it's going at the end, that solving it using an energy technique rather than a Newton's second law F equals ma technique, this is a much easier way to do it.